Hello, and welcome to the Sleepy Thinker. I'm so glad you're here. Whether your day has been long, your thoughts restless, or you simply love dozing off to the gentle hum of science, this video was made just for you. Tonight, we'll be drifting quietly through the stars to explore one of the strangest facts in all of physics. Why light, the most familiar thing in our world, is a speed limit. But before we begin, I'd love to know, where in the world are you listening from? And what time? Is it right now where you are? Are you settling in under city lights, or tucked away somewhere silent and calm, maybe with a warm cup in hand? If you enjoy these sleepy science wanderings, I'd be truly grateful if you gave the video a little like and tapped the subscribe button. It helps other curious, tired minds find their way here and lets me keep creating more of these star-soaked journeys for you. Of course, I hope this video doesn't keep you up. But if it does, well, at least you'll drift off knowing a little more about how our universe whispers its secrets. Not such a bad trade. Really. So settle in. Close your eyes if you like, and let's begin a gentle journey through the strange, beautiful mystery of light, and why it always seems to be rushing through everything, as if the universe gave it no choice but to hurry. Light is one of those things we think we understand until we try to explain it. You flip a switch, there it is. It fills the room, lets you see your cat's judgmental expression, and keeps your phone glowing long past bedtime. But what actually is it? A wave? A particle? A ghost? Some kind of cosmic courier with a delivery schedule too strict for its own? Good. The short answer is yes. And also, let's take a soft, thoughtful walk through what light really is. Because before we can understand why it has a speed limit, we need to understand what's doing the speeding. Let's begin with photons. They're the building blocks of light, tiny packets of energy that zip through space at the fastest speed the universe allows. But these messengers are strange. They aren't particles like marbles or grains of sand. They have no mass, they never rest, and they don't follow the usual rules. And yet, they're also waves, not waves like oceans or curls of hair, but electromagnetic waves, vibrations of electric and magnetic fields, weaving through space in perfect harmony. These fields oscillate at right angles to each other and to the direction of the wave's motion, a sort of elegant, invisible dance. Here's what makes light special. These waves don't need anything to move through. Most waves, sound waves, need air. Water waves need water. Even the little wave you give a neighbor needs a fence to lean on. But light just goes. It moves through the vacuum of space effortlessly, which is why we can see the sun over 90 million miles away. It's light traveling across empty space to touch our eyes without stopping once. And that's not all. Light doesn't just come in one form. The light we can see, what we call visible light, is only a tiny sliver of a much larger spectrum. Imagine a piano stretching for miles. Visible light would be just a handful of keys in the middle. On one end of this electromagnetic keyboard, radio waves long, slow undulations that can stretch for kilometers. On the other end, gamma rays, sharp, high-energy spikes born near exploding. Stars and nuclear reactions. In between, we find microwaves, infrared, which your TV remote uses, ultraviolet, which burns your skin, and X-rays, which peer through your bones, though never through your laundry basket. And yet, despite all their differences, every kind of light travels at the same speed in a vacuum, roughly 299,792,458 meters per second, or just under 300,000 kilometers per second. It's such a massive number that it almost feels like the universe is joking. How fast is that, you ask? And the universe answers, yes. To put it in sleepy terms, if light were a runner, it could circle the Earth more than 7 times in a single second. Not bad for something with no legs. But here's the curious part. Light doesn't always move that fast. In a vacuum, light travels on a clean track with no traffic. But when it enters a medium like water, or glass, or diamond, it slows down. Not because it's tired, but because it's bumping into atoms along the way. It's like walking through a crowded party. You're still heading in the same direction, but there's a lot more weaving and sidestepping involved. This slowing is what causes refraction, the bending of light when it moves from one substance to another. It's why a straw looks bent in a glass of water, and why diamonds sparkle the way they do. But here's the twist. Even though light appears to slow down, the individual photons still move at the same speed between atomic interactions. Just taking a more complicated path, like someone trying to speed walk through a dance floor full of enthusiastic uncles at a wedding. Now, let's talk a little about color. When we look at a rainbow, or a prism, or even the rainbow shimmer on a puddle of oil, we're seeing light split into its various wavelengths. Each color of visible light has a different wavelength. Red is long and lazy. Violet is short and twitchy. But all of them, red, green, blue, orange, indigo, are still photons. Still electromagnetic. Waves, just vibrating at different frequencies. Your eyes have special cells, called cones, tuned to specific ranges of those frequencies. That's how you see color. It's not that the apple is red, it's that it reflects a wavelength your brain interprets as red, while absorbing the others. Color, in a way, is just your brain's best guess based on which vibrations make it to your retina. And as if all that weren't magical enough, light also has no rest mass. Unlike you, or me, or your deeply skeptical cat, light doesn't need energy to start moving. It always moves. It has no choice. If a photon were ever to stop, it wouldn't just be resting. It would cease to exist. Its motion. Or nothing. That's not just poetic. That's physics. So here we are talking about massless packets of energy that behave like both particles and waves, travel at a cosmic speed limit, bend through glass, bounce off mirrors, and deliver the miracle of vision to our brains. And that's just scratching the surface. But for tonight, let's hold on to this one image. Light as a restless traveler made of no substance but energy, never stopping, never sleeping, always tracing the outlines of our world. It shows us the stars, the faces we love, and the pages of the stories we hold close. And it does all this while following one of the universe's strangest rules, a speed it will never break and never fall below. Light isn't just what helps us see, it's how the universe whispers itself into our open, waiting eyes. Let's take a gentle step back in time. Long before lasers and satellites, before physicists had equations or tools, imagine a world lit only by flame and stars. A world where understanding something like the speed of light seemed almost absurd. For most of human history, people believed light was instantaneous. You lit a candle, the room lit up. The sun rose, the world turned gold. No delay. No wait, it just happened. Even the ancient Greek philosopher Empedocles, one of the rare few who guessed that light might have a finite speed, was mostly ignored. Aristotle, whose opinions had a habit of sticking around for far too long, thought light was instantaneous, and for centuries, that was the end of the story. Curiosity shelved, but then came Galileo. And Galileo wasn't one to take anyone's word for it. He liked to poke things, drop them off towers, and aim telescopes at the moon. And in the year 1638, he decided to try and measure the speed of light in what might be the most adorably ambitious experiment in history. The idea was simple. Galileo and his assistant each took a lantern, covered it, and stood on distant hilltops about a mile apart. Galileo would uncover his lantern, and as soon as his assistant saw the flash, he'd uncover his too. In return, Galileo would then measure the time between sending his lantern signal and seeing the flash sent back, even under the best circumstances. This experiment was wildly optimistic. The average human reaction time is about a quarter of a second, but light takes less than a 10,000th of a second to travel a mile. It was like trying to measure the speed of a bullet with a sundial. Still, you have to admire the effort. Galileo, unsurprisingly, concluded that if light did have a finite speed, it was far too fast for him to measure. And he was absolutely right. But for the first time, someone had dared to ask the question. A few decades later, a Danish astronomer named Ole Rachmer would accidentally stumble onto the answer, not by using mirrors or lanterns, but by watching something unimaginably far away, the moons of Jupiter. In the year 1676, Rachmer was carefully tracking Io, one of Jupiter's many moons, a small world zipping around the gas giant like a precise celestial clockwork. By observing the moments when Io vanished behind Jupiter and when it reappeared, he began to notice something strange. The timings weren't always consistent. Sometimes Io showed up a little early. Other times it lagged behind. At first, this seemed like bad data, a flaw in the method. But then Rachmer had a quiet, brilliant thought. What if it wasn't Io that was changing? What if it was us? What if the reason Io seemed late or early had to do with Earth's position in its orbit, with light having farther to travel when we were on the far side of the sun? And just like that, the idea of light having a measurable speed began to take real scientific shape. From these subtle delays, Rachmer estimated that it took light about 22 minutes to cross the full diameter of Earth's orbit, a distance we now know is around 186 million miles. And remember, didn't have modern clocks, or accurate distances, or satellites beaming down signals from the sky. Still, he got close. Not perfect, but revolutionary. He'd shown the world that light takes time. Not much, but enough to matter. Fast forward to the early 1800s. A French physicist named Hippolyte Fizeau tried something a bit more grounded. His method involved three things: a beam of light, a rotating toothed wheel, and a mirror placed several miles away. Here's how it worked. A light beam passed through a gap between the teeth, traveled to the distant mirror, and bounced back. If the wheel spun slowly, the returning beam would pass through the same gap and be visible again. But as the wheel spun faster, the returning light would arrive just as a tooth blocked. The path and the beam would vanish. By adjusting the speed of the wheel to the point where the light beam was completely blocked, Fizeau could calculate exactly how long it took the light to make the round trip. With the distance known and the rotation speed measured, he estimated the speed of light at about 193,000 miles per second. That's impressively close to the modern value, especially for an experiment involving mirrors, gears, and a lot of cleverness. Not long after, another physicist, Léon Foucault, refined the method even further. Instead of wheels, he used spinning mirrors, which allowed for even more precise control. Foucault not only confirmed that light had a finite speed, he also discovered something crucial. Light slows down when it travels through water compared to when it travels through air. That single observation was a critical clue, a hint that light interacts with materials in ways that change how fast it can go. But perhaps the most iconic name in the race to measure light was Albert Michelson. In the late 1800s. Michelson took Foucault's method and pushed it to extraordinary levels of precision. He used long tunnels, perfectly aligned mirrors, and incredibly fine-tuned timing instruments to measure the speed of light with an accuracy no one had ever achieved. His results stunned the scientific world, and in 1907, he became the first American to win the Nobel Prize in Physics. Not a bad reward for someone who spent his life chasing beams of light around with mirrors. Today, of course, we have tools that Galileo and Rachmer could never have imagined. Lasers, atomic clocks, satellites, and measurements so accurate that we no longer even define light speed by measuring it directly. In fact, since 1983, we've flipped. The entire equation. The meter basic unit of distance is now officially defined as the distance light travels in 1,299,792,458th of a second. We don't use light to measure things anymore. We use light as the very thing that defines our measurements. But it all began with lanterns and moons and people wondering whether the universe might be a little slower than it looks. That's the quiet beauty of it. The speed of light isn't just a number, it's a story of curious minds, imperfect tools, and elegant persistence. It's a tale written across centuries, from windswept mountaintops to candlelit observatories, to satellites floating in orbit. It's proof that even the fastest thing in the universe couldn't outrun human curiosity. So now that we've met our speedy little photon friend and followed the long, patient journey to measure its pace, let's ask the question that keeps physicists awake at night. Why doesn't light just go faster? After all, 299,792,458 meters per second feels oddly specific. Why not a clean, round number like 300 million? Why not 500 million? Or even infinite? Why does light, a weightless, ethereal bundle of pure energy, have to follow a speed limit at all? To answer that, we'll need to take a gentle stroll into one of the most beautiful and mind-bending parts of physics, electromagnetism. More specifically, we need to talk about a man named James Clerk Maxwell. In the 1860s. Maxwell took everything scientists knew about electricity and magnetism, think Benjamin Franklin's lightning rods and Michael Faraday's spinning coils, and wove it all together into 4 elegant equations. Today, we call them somewhat unimaginatively Maxwell's equations. They describe how electric and magnetic fields behave, how they move, how they shift, how they dance. Now don't worry, no one's going to quiz you at bedtime. You don't need to know the math. Here's the dreamy part. When Maxwell combined those equations, he noticed something hidden in the math. They predicted a wave. A self-sustaining wave that would naturally form when electric and magnetic fields wiggled in just the right way. And this beautiful, invisible ripple would travel at a very specific speed. So Maxwell did the math. He plugged in the constants, the known values for electric and magnetic properties of space, and out came a number. That number? You guessed it. 299,792,458 meters per second. The speed of light. Maxwell was stunned. He hadn't just discovered a wave. He had discovered the wave. The very nature of light itself. Light, he realized, was an electromagnetic wave, a ripple of electric and magnetic energy moving through the vacuum of space at a speed dictated not by coincidence, but by the very structure of reality. Let that settle in your chest for a moment. Light doesn't travel at that speed because it's fast. It travels at that speed because the universe is built in such a way that it can't do anything else. The speed of light isn't random. It isn't arbitrary. It's carved into the laws that govern all space and time. If electric and magnetic fields exist, and they most certainly do, then light must move exactly as fast as it does. Anything else would break the rules. So now we know. Light moves at the speed it does, because that's the only speed electromagnetic waves can move through a vacuum. Any faster or slower, and the math wouldn't work. The universe wouldn't work. But now comes the next mystery. Why can't anything go faster than that? In daily life, speed feels optional. Your car can go 90. It can go 100. If you're feeling bold, 110. But light? No matter how much energy you give it, no matter how clever your spaceship, you'll never beat that cosmic limit. To understand why, we need to call on someone you've probably heard of. Albert Einstein. In 1905, Einstein published his special theory of relativity, and with it, he rewrote our understanding of space and time. One of his key ideas was this: the speed of light in a vacuum is the same for all observers. Number. Matter how fast they're moving. That might sound tame, but it's absolutely wild. Imagine you're on a train moving at 90%. The speed of light, highly impractical but perfect for a thought experiment. You turn on a flashlight. You might expect the beam of light to travel faster for someone standing on the platform. After all, your train is already moving, and now the light is moving on top of that dot. But no. Here's the mind-bending part. Both you and the person on the platform will measure the light beam's speed as exactly the same 299,792,458 meters per second. Not a hair more. Not a flicker less dot to make that possible. Reality itself must bend. Around the rule, time slows down. Lengths shrink dot as your speed increases. The universe quietly adjusts its ticking, shifting time and space to make sure that no matter how fast you go, you'll never see light speeding up or slowing down. And if you, a brave astronaut, decided to chase the speed of light itself, you'd run into a problem. Not as you go faster, your mass increases not in the too many cookies sense, but in the deeply inconvenient physics sense. Each small boost in speed requires more and more energy. The closer you get to light speed, the more effort it takes to move just a little bit faster dot, until eventually your mass approaches infinity, and to push something with infinite mass requires infinite energy. That's a tall order, even for the most ambitious traveler dot, so no matter how hard you try, you can get close to light speed, but never touch it. Never catch it. Never pass it. You can chase the light, but it will always stay just out of reach. That's why the speed of light isn't just a number. It's a boundary, a cosmic speed limit, the fastest anything, energy, information, or mass can ever travel dot. It's not just fast. It's fundamental, a built-in constraint, woven into the very structure of space and time. And here's something peaceful to consider. If the speed of light weren't limited, everything would fall apart. Causality, the simple idea that causes come before effects, would no longer hold dot in theory. You could see an effect before the cause that made it. You could send information backwards through time dot. It would be chaos, paradoxes, reality, unraveling into contradiction. But the universe protects us from that kind of nonsense with this beautiful little rule. This upper speed cap keeps everything stable, predictable, calm dot. No matter what else changes, the speed of light stays the same dot. So next time you watch a sunset or gaze at the stars overhead, remember, those beams of light didn't just happen to arrive. They obeyed a rule, one etched deep into the bones of physics. A rule that says, this far, no farther dot. It's a limit, yes, but it's a limit that gives the universe its shape, its order, its quiet beauty. Light doesn't travel slower because it's lazy, or because it lacks strength dot. Travels as fast as anything can, because that's the pace at which reality can still make sense dot. Bound to a perfect speed, not too much, not too little, but just enough to keep time moving forward, keep cause and effect aligned, and keep the world from falling into a tangle of impossibility. And honestly, for something that dances across the cosmos at nearly 300,000 kilometers per second, I'd say that's a pretty graceful pace. Albert Einstein had a gift for taking the deepest truths of reality, flipping them inside out, and making them feel like they had always been obvious, like the universe had been whispering them all along. And he just happened to listen dot in 1905. When Einstein introduced his special theory of relativity, he didn't just tweak the rules of physics. He rewrote them. And at the center of his theory was a bold and unsettling claim. The speed of light in a vacuum is constant, not generally constant, not mostly consistent, not as long as nothing's moving too fast. Absolutely, unequivocally constant. For everyone, everywhere. Always. It sounds tame, like something you might half hear as you're drifting to sleep, but it breaks everything you think you know about motion and time. Let's walk through a thought experiment. You're on a spaceship, floating peacefully through the void. In your hand, a flashlight. You click it on. A beam of light shoots forward. Say it with me. 299,792,458 meters per second. Now, imagine your co-pilot is flying past you in another spaceship, moving at half the speed of light. From their perspective, you and your ship are zooming by like a blur. But when they measure the speed of that same beam of light you just turned on, they don't see it going faster, or slower, or changed at all. They measure it at exactly 299,792,458 meters per second. The same dot, always the same dot. And that's weird. Like deeply weird in everyday life. Speeds add up. If you're walking on a moving walkway at the airport, your total speed is your walking speed plus the belt's motion beneath you. But with light, it doesn't matter how fast you're moving, how fast the flashlight is moving, or even whether the observer is standing still or flying sideways at ridiculous speed. The speed of light stays perfectly, frustratingly the same dot. So what gives? Einstein's answer was simple and beautifully unsettling. It's not the speed of light that adjusts. It's everything else. Time, space, the way moments pass, the shape of distance, the rhythm of existence itself. All of it bends, twists, and stretches to preserve that one sacred number. Compared to someone standing still, time doesn't just feel different for a fast traveler. It is different. This isn't just a thought experiment. It's real. It's measurable. Let's say you're on a spaceship traveling at 90% the speed of light. To you, everything feels perfectly normal. You eat snacks, read a book, maybe wonder why you didn't pack more socks. But when you return to Earth, you might find that years, even decades, have passed. Not for you. You've only experienced a short trip. But for everyone else, time has marched on without you. This isn't some theoretical quirk that only lives in textbooks. We've tested it. Particles called muons are created high in Earth's atmosphere when cosmic rays collide with air molecules. They decay very quickly, within microsecond. But when they're moving near the speed of light, their internal clocks slow down. They last longer, long enough to reach the ground, long enough for us to detect them. Time stretches for them as they move. That's time dilation in action. Now, let's talk about length contraction, the strange twin of time dilation. When you move at high speeds, objects in the direction of your motion actually appear shorter, not as an optical illusion, but as a physical, measurable change. If you were flying in a spaceship close to the speed of light, your ship would literally measure shorter along the direction it was traveling. And don't worry, you wouldn't feel squished like a folding chair. These effects only become noticeable when you're traveling near the speed of light. For everyday things, cars, planes, joggers, the change is so tiny it might as well not exist. But when you approach light speed, space itself begins to compress. Then there's something with a beautifully strange name. Relativity of simultaneity. Why? It sounds like a riddle. But it's actually a bit of mental poetry. It means this. Two events that seem to happen at the same time for one person might not be simultaneous for someone moving relative to them. Here's a classic example. Imagine a train racing down the tracks at high speed. In the middle of the train, a light bulb flashes to someone sitting inside. The light spreads out and reaches the front and back of the train at the same moment. But to someone standing on the platform, it's different. Because the train is moving, the front of the train is rushing away from the light, and the back is moving toward it. From this point of view, The light hits the back of the train first dot, and both people are right. Time and space are no longer absolute. They're flexible, local, relative. All of this, the time stretching. The distance is shrinking. The breakdown of simultaneity. It all happens to preserve one sacred rule, that the speed of light must remain constant dot. It's as if the universe looked at this number 299,792,458 meters per second and said, everything else can bend, but this must not break. It's like a cosmic contract, dot. In exchange for letting light remain steady, the universe agrees to twist and warp everything else around it, dot. It's a delicate balancing act. But it works, dot, and it keeps causality order of events intact. Here's a soothing thought. This speed limit, this sacred maximum, is what protects our understanding of time. Because light can only move so fast. Information can only move so fast, dot, and that means you can't witness something before it happens. You can't send a message into your own past. The speed of light gives time its forward direction. Without it, the timeline would unravel. Paradoxes would pile up like socks in a teenager's bedroom. Instead, the universe gently says, no, let's not do that. Let's have order. Let's have a maximum speed. And let's make it sacred. And this is where Einstein's work shines brightest. He didn't just describe the speed of light as a limit, dot. He showed that it is the cornerstone of reality itself, the scaffolding that holds time and space together. Today, we use Einstein's equations in ways he probably couldn't have imagined. GPS satellites rely on them to calculate your exact location. Without relativistic corrections, your phone could think you're floating in the middle of the ocean. Particle accelerators use his equations to guide subatomic particles as they circle at near light speeds. Astronomers use them to decode the messages of galaxies billions of light years away. All of it rests on this strange but constant truth. Light has a maximum speed. And that speed is the same for everyone, dot. So the next time you see sunlight filtering through your window, or a lighthouse beam cutting softly through the dark pause, and remember, that beam of light isn't just warmth. It isn't just visibility, dot. It's a whisper from the geometry of spacetime itself, a quiet agreement between matter and meaning, a contract written in photons, dot. And no matter how far you go, no matter how fast you run, you'll never outrun that beautiful, invisible truth. Where you will, light will always find you at the same pace, unchanged, unwavering, eternally on time, dot. So far, we've explored light itself, what it is, how we measured its speed, and why the universe insists on giving it such a specific, unbreakable limit. But now, let's gently zoom out and look at what this cosmic speed limit does to reality. Because once you realize that light can't go any faster than it already does, the implications are surprisingly far-reaching, and in many ways, quietly beautiful. Let's begin with something fundamental. Time. Not the kind on your kitchen clock, but the kind that stitches together events, memory, and meaning. The speed of light gives time its shape, dot. It sets the rules for what can influence what. It says to the universe, you may only connect these dots if there's time for light to travel between them. This idea forms the foundation of something physicists call the light cone, dot. It's not a snack. And it's not a LAMPSHADE, dot. A way of mapping what parts of space and time can be causally connected. Imagine this. You're standing alone in a field. You strike a match. That tiny spark sends out light in all directions, a ripple of information, expanding through space. The furthest anything can be affected by that match, immediately or eventually, is limited by how far light can travel from that moment onward. If someone is standing 100 light years away, they won't even know the match was lit until 100 years have passed. Now flip the scene. You're still standing in the field, but this time, you're waiting. The only events that could possibly affect you in this very moment are the ones whose light has had time to reach you. That's your past light cone, everything that could have caused your present experience. The light cone isn't just a diagram. It's the border between what's possible and what's not. If something happens outside your light cone, it isn't just too far. It's too far in time, no signal, no sound. No whisper can reach you from that event, not yet. For you, it's as if it doesn't exist at all, not until the light arrives. This idea, this soft, quiet limit shapes our entire understanding of the universe, it tells us there's no such thing as instant communication. No perfect, shared now across the stars. Every moment is local. Every present is a little different, depending on where you are. And light speed is the rule book that makes it all consistent. Think about how this shapes your view of the night sky. When you look up at the stars, you're not seeing them as they are. You're seeing them as they were. The light from the nearest star system, Alpha Centauri, takes more than 4 years just to get here. If something happened there last week, some flash, some collapse, we won't know for several more years. And that's just next door. Look farther. The light from the Andromeda galaxy takes over 2 million years to reach us. So when you look at it glowing faintly in the sky, you're seeing it as it looked when early humans were still learning to make tools. Beyond that, we see light from galaxies billions of years away from before our sun even existed. And yet, it all feels so close. The stars twinkle. The galaxies glow. They seem right there, but they're not. What we see is a history written in light, traveling across time at its own patient pace. And this delay, this gentle slowness, is what allows astronomers to be time travelers. Every telescope is a time machine. Every lens a portal into ancient epochs, all because light doesn't move instantly. Its limit gives us access to the past. There's also something elegant about how this delay preserves causality. You can't affect something unless there's time for a signal to get there. That's not just a rule. It's a safeguard. It protects logic, prevents paradoxes, keeps time moving in one direction. It's the universe's quiet way of saying, let's keep things sensible. Because without this speed limit, chaos would unfold. If you could send signals faster than light, you could at least in theory send messages to your past self, like, don't eat that suspicious burrito. And if you listened in time, you'd have no reason to send the message. That kind of loop where cause destroys itself is exactly the kind of nightmare that keeps theoretical physicists awake at night. And not in a cozy way. Thanks to light's cosmic speed cap, those paradox loops never happen. You can't outrun your own consequences. Events unfold in order. The past stays behind. The future waits ahead. It's not just the flow of time, it's the structure of time. A framework the universe refuses to bend, and it affects more than just distant galaxies or thought experiments. It shows up in your daily life. Think about communication. When you make a phone call, send a message, or stream a late-night video, you're working with light even if you don't think about it. If you're talking to someone on the other side of the planet, there's a slight delay, tiny, but measurable. That signal, traveling as electromagnetic waves, often bounces through satellites or zips through fiber optic cables. These pulses of light move at or near the cosmic speed limit. But Earth is big, and even light, as fast as it is, takes time. Now think even bigger. When NASA sends a command to a rover on Mars, that signal can take anywhere from 4 to 20 minutes to arrive, depending on where the two planets are in their elliptical dance. So, if the rover stubs its robotic toe on a Martian rock, the scientists won't know until nearly half an hour later. There's no real-time joystick, no instant remote control. The rover has to make decisions on its own. Because light speed says, you're on your own out here. Even your favorite streaming platform, your quiet documentaries, your cozy movie nights, they all depend on this limit. Every pixel, every frame, has to travel from a server across continents and oceans, through glass cables and metal switches, as pulses of light. And no matter how advanced the tech, none of it can outrun the universe's built-in pace. It might sound like a constraint, but really, it's a kind of harmony. The speed of light gives us a universe where effects follow causes, where the past is fixed and the future is waiting. It gives shape to space and time. It turns an infinite, formless void into a structured, understandable world. And while it may seem strange that the fastest thing in the universe is also what slows down how quickly we can know something happened, those tiny delays. There, what make the universe knowable? They give us perspective. They create distance. They offer a pause, a little breath between moments, a little space to think, to wait, to rest. But let's imagine for a moment that you're not the kind of person who takes no for an answer. You've heard all about this cosmic limit, this traffic rule carved into reality. And your first question is, what if we ignore it? Could anything in any strange corner of the universe ever go faster than light? It's a tempting thought. After all, humans love to push boundaries. We've broken the sound barrier. We've hurled robots at Mars. We've built machines that split atoms and stitch genomes. So what's stopping us from finding some kind of shortcut? Some hidden pathway that zips past 299,792,458 meters per second? Let's start with a quirky idea from the deeper corners of theoretical physics. Tachyons. Tachyons are hypothetical particles that appear in certain mathematical models, and they come with a strange feature. They can only travel faster than light. They can't slow down to reach the speed of light, because that, for them, is the barrier in the opposite direction. It sounds thrilling, a particle that naturally ignores the rules, racing through the cosmos like a hyperactive squirrel on a cosmic espresso shot. There's just one small hitch. No one's ever seen one. Not in a lab. Not in deep space. Not even hiding between the lines of messy equations. They're like a cosmic rumor, always whispered, never confirmed. And even if tachyons did exist, they'd come with their own baggage. Because if you could use them to send messages, you could violate causality, meaning you could send a message into the past. And if you've ever watched a time travel movie, you know how that goes. Grandparents vanish, timelines tangle, and logic collapses. So, for now, tachyons live in a little box labeled interesting. But probably not. But what about other fast phenomena? Let's turn to something that's not hypothetical at all, something Einstein himself called spooky. Quantum entanglement. One of the strangest and most misunderstood features in all of physics. When two particles are entangled, measuring, one seems to instantly affect the other, no matter how far apart they are. You measure one here on Earth, and it's twin light years away. On the far side of the galaxy reacts in perfect sync. It feels like a cosmic cheat code. Surely, this must be faster than light. Wellies, and also, no. Here's the key. Entanglement does create instant correlations, but it doesn't transmit usable information. You can't choose the outcome of the measurement. And if you can't choose, you can't send a message. It's like two people flipping identical coins on opposite ends of the universe, and somehow always landing the same. Mysterious? Absolutely. But communicative? Not really. Neither flipper can use it to say hello. Einstein was deeply troubled by this. He famously called it spooky action at a distance. And yet decades of experiments have confirmed it's real. Particles do behave this way. But the universe, in all its spooky cleverness, still respects the speed limit. Then there's something a bit glowier and a little weirder. Cherenkov radiation. It happens when a charged particle moves through a medium like water faster than light can move through that same medium. Yes, you read that right. Light doesn't always travel at its maximum speed. In glass, water, or plastic, it slows down slightly due to atomic interactions. So if a particle moves faster than that reduced speed, it creates a sort of light shock wave, like a sonic boom. But for photons, that's the eerie blue glow you sometimes see in nuclear reactors. But no laws are broken here. Nothing is actually going faster than light in a vacuum. No one has crossed the sacred line. It's just that inside certain materials, light slows a little, and some particles manage to sneak past. Call it a technicality. So what about going further? What about warp drives, space folding, the beloved dreams of science fiction? Could we bend space itself instead of speeding through it? Well, in theory maybe. In the 1990s, physicist Miguel Alcubierre proposed a mind-bending idea. What if, instead of moving the ship, we moved the space around it? You'd compress space in front, expand space behind, and let the ship surf the wave. Technically, the ship wouldn't break the speed of light because it wouldn't be moving through space at all. Space itself would be moving. It's clever, elegant, even. But there are a few snags. First, you'd need something called negative energy density, a kind of exotic matter that, so far, only exists in speculation and equations. We don't know how to make it. We don't even know if we can. Second, the energy required. Well, let's just say it's not pocket change. Some estimates suggest you'd need the mass energy of Jupiter just to move a grapefruit. So for now, warp drives remain firmly in the realm of imagination. Great for storytelling, tricky for engineering. There's also the idea of wormholes, tunnels through spacetime that could, in theory, connect two distant points instantly, like a cosmic shortcut. A fold in the map. Again, the math allows them, but the obstacles are steep: stability, exotic matter, time paradoxes. Trying to hold one open would be like building a suspension bridge out of soap bubbles and hope. And even if you could make one work, it wouldn't technically be faster than light travel. You'd just be taking a shorter path. Light still wins the marathon. You just found a secret alleyway. So, where does that leave us? Despite decades of dreaming and centuries of scheming, nothing with mass or information has ever been observed traveling faster than light. Every time we think we've found a loophole, a clever trick, a cheat code, the universe calmly steps in, with a raised eyebrow and a chalkboard full of equations. And maybe that's not such a bad thing. The speed of light might seem like a frustrating restriction, a locked door at the edge of possibility, but in truth, it's more like a safety rail. It keeps the universe from unraveling into paradox, chaos, and spaghetti timelines. It gives us structure. It gives us order. It gives us serenity. Because no matter how weird the cosmos gets, no matter how strange or spooky or surreal, there are still boundaries. There are still rules. There is still light. Swift, silent, steady. Leading the way, and moving as fast as anything can. And maybe, just maybe, that's enough. By now, you've probably noticed a pattern. The speed of light, this oddly specific number, isn't just a rule written in equations. It's a cornerstone, a boundary, a cosmic constant woven into the very bones of reality. But what if it's more than that? What if that mysterious number 299,792,458 meters per second isn't just a speed limit, but a quiet clue to the universe's deeper structure? Not just a number in physics class, but a bridge between space and time, between energy and mass, between motion and stillness. Let's take a gentle walk into one of the more philosophical corners of physics. No equations needed. You can keep your slippers on. Here's one of the more fascinating ideas in modern physics: The speed of light is not just the pace of a photon. It's a conversion factor, a kind of cosmic translator dot. It tells us how space and time relate to each other. It's what lets us swap distance for duration, and vice versa. That's why light years exist. A light year isn't time-light's distance. It's how far light travels in 1 year. You see this same constant in Einstein's famous equation, E equals mc. There, c squared acts as a bridge between energy and mass. It tells us how much energy is tucked inside a speck of matter. But this number, c, keeps showing up everywhere in time dilation, length contraction, black hole equations, the bending of space-time itself. And it's not a coincidence. It's constant. Reappearance is the universe nudging us, saying, this isn't just a speed. This is the structure. Try imagining the universe as a great, woven fabric, not of space and time, but of space-time.1 fabric. Not two threads side by side, but one seamless cloth. This isn't science fiction jargon, it's Einstein's actual model. In relativity, space and time aren't separate things. They're unified. When you move through space, you're also moving through time dot, and the faster you go through space, the slower you move through time. Gravity doesn't just pull. It bends the space-time fabric dot. Can light? Light is the thread that stitches it all together. Here's where it gets poetic. The speed of light is the exchange rate between space and time. Think of it like a currency counter at a train station, but instead of dollars for euros, you're trading meters for seconds. You walk into that booth and say, how far is 1 second? And the universe replies, about 299,792,458 meters. That's the meaning behind light years. Again, a time-based term we use to measure space. They're deeply, inseparably connected. And the speed of light is what keeps them in sync. Now, consider this calming thought. When we say that nothing can go faster than light, we're also saying that nothing can disturb the sacred relationship between time and space, that the speed of light is what defines that relationship. It keeps the quilt of reality neatly sewn. It assures that causality happens before and after doesn't unravel. It's not just a rule. It's a kind of cosmic etiquette. There's something serene about that. Because it means the universe isn't chaotic even when it's confusing, wherever you are in space. However fast you're going, c is always the same. The universe plays by its own rules, but it does so consistently that one constant holds firm even near black holes, even in the hearts of galaxies. And physicists treat it with the reverence it deserves. In many natural unit systems, they even set c equals 1. Not because they're being lazy, but because it simplifies everything. It makes space and time symmetrical, easier to compare, cleaner to describe, elegant to calculate. When c becomes 1, time and distance become equal players. The math stops shouting and starts singing. And this leads us to an even more curious and beautiful idea. Maybe the universe wasn't built so that light can move. Maybe the universe was built around light speed. Maybe c isn't just a limit. Maybe it's the scaffolding. Now hold this final thought gently. When a photon particle of light moves, it does so at the speed of light. And relativity tells us that as things move faster, their experience of time slows down. So for something moving at the speed of light, time stops altogether. From a photon's perspective, the moment it's emitted and the moment it's absorbed happen at the same instant. No journey, no waiting, no passage. Just presence. A photon is a moment, not a traveler. It exists only in motion. It can't be at rest. It doesn't age. It doesn't see time flow. It just is. And that's the poetic truth at the end of all of this. Light doesn't just move through the universe. It defines the universe as it moves. The speed of light isn't something light decides. It's something the universe demands. Even the way we define our most basic units of measurement now revolves around that number dot. Since 1983, the meter has been defined not by a ruler or a rod, but by light. Specifically, 1 meter is the distance that light travels in 299,792,458 of a second. That's not just poetic, that's precise. We've made light the measuring stick against which all other rulers are compared. It's our gold standard for both time and space. And maybe that's the most grounding truth of all. In a universe filled with dark matter, quantum uncertainty, and uncharted infinities, there's something beautifully fixed. The speed of light is a constant you can build your world on. Because we quite literally do. So the next time you see a flicker from a candle or soft starlight filtering through your window, know this: you're witnessing more than just brightness. You're watching a law of nature unfold, a quiet message from the very geometry of space-time, a reminder that even in a vast and mysterious cosmos, some things stay steady. Light doesn't just illuminate the world. It sets the rhythm of the cosmos. And maybe, just maybe, on a quiet night, as ancient photons drift down from stars long gone, you'll hear the universe whisper in its own eternal language, softly, steadily, at exactly 299,792,458 meters per second. By now, you've seen how the speed of light isn't just a textbook footnote. It's the pulse of reality, the thread that stitches space to time, the steady metronome that keeps the universe in rhythm. But here's what might surprise you. The speed of light isn't just something that governs galaxies and black holes. It's woven into your daily life, too. Even if you've never piloted a spaceship, built a particle accelerator, or stared at quantum equations, you still live in a world shaped by light's cosmic speed. Let's start close to home. Your phone. Yes, that glowing rectangle you might be using right now. Every time you tap the screen, stream a video, or send a sleepy emoji to a friend, you are using light. Specifically, light traveling through fiber optic cables. These delicate strands of glass or plastic form the backbone of the internet. They stretch across oceans and continents, forming a global web that moves information at nearly the speed of light. When you load a web page, you're not waiting for a distant server to think. Slowly, you're waiting for pulses of light, tiny flashes, carrying digital 1 south and 0 south to race through cables, bounce through routers, and land on your screen. And while light slows a bit when traveling through fiber, about 2/3 its vacuum speed, it's still staggeringly fast. We're talking hundreds of thousands of kilometers per second. That's how your podcasts, cat videos, weather updates, and bedtime music arrive in the blink of an eye. But those fiber optic cables aren't just shuttling data. They're also helping us keep time. One of the most precise systems we rely on every day is deeply tied to the speed of light: GPS. When you use your phone to find the nearest bakery, your device connects to at least 4 satellites orbiting high above Earth. Each satellite sends a signal stamped with the exact moment it left. Down to the nanosecond. Your GPS receiver compares the timing of these 4 signals to figure out where you are. It's like asking 4 friends how far they are from you, and using their answers to draw a map around yourself. But here's the twist. For GPS to work, we have to account for relativity. The very theories we've been whispering about all this time. Those satellites are moving quickly relative to Earth's surface, which means their clocks tick slightly slower due to special relativity. But they're also farther from Earth's gravity, so their clocks tick faster thanks to general relativity. Both effects are tiny, but if we didn't account for them, your GPS would be off by kilometers every single day. Thanks to light and our understanding of how it behaves, your phone can guide you to within meters of your destination. That's the speed of light at work, not in a particle accelerator, not in a black hole simulation, but in your hand, thanks to Einstein's insights and the rock-solid constancy of light speed. Your GPS can guide you right to that croissant you didn't know you were craving. But let's zoom in even closer. Closer than satellites. Closer than cables. Let's look at your eyes. Vision itself is built entirely on the behavior of light. When you look around, what you're really seeing are photons bouncing off objects and entering your eye. They pass through the cornea and lens, get focused onto the retina, and trigger chemical changes in light-sensitive cells called rods and cones. Your brain then takes those tiny electrical signals and weaves them into the vivid, colorful experience of a world, a tree, a sunset, your oddly judgmental houseplant. All of this depends on the speed of light, how fast it travels, how it bends through materials, how it interacts with atoms in your retina. Even your sense of depth comes from a timing trick, a barely noticeable delay between photons reaching each eye, and your brain doing the comparison. Now consider refraction, what happens when light enters a new material and slows down, changing direction. It's why a straw looks bent in a glass of water, why heat shimmers on a distant road. But it's also the foundation of our most important lenses, eyeglasses, microscopes, telescopes, cameras. Every time you snap a photo or read a book through glasses, you're using the bending of light to see better. Even your microwave oven owes its magic to light. Microwaves are just a lower frequency form of light, part of the same electromagnetic family. Inside your oven, these waves bounce around, jiggling water molecules in your food and heating it up. Without our deep understanding of electromagnetic waves, reheating leftovers would be a much messier affair. Now, take a cozy step into telecommunications. Your favorite radio station? That's light too, just with longer wavelengths. Radio waves, Wi-Fi, Bluetooth, television broadcasts, all of them are forms of electromagnetic radiation, zipping invisibly through space, obeying the same rules as starlight and lasers. And in medicine, light plays a quiet but vital role. X-rays, ghostly bone images are high-frequency electromagnetic waves. They pass through soft tissue, but are absorbed by bone, creating that eerie but helpful snapshot. MRI machines, while they don't use visible light, rely on electromagnetic fields to reveal stunningly detailed images of the inside of your body. In short, lighter, its extended electromagnetic family, is quietly working behind the scenes of almost everything you do. It's how we see, how we communicate, how we navigate, how we cook, how we diagnose illness, how we stream movies and scan barcodes and send sleepy emojis. And speaking of scanning, let single quotes S return to the stars. Everything we know about the universe beyond our solar system has been delivered to us by one thing: light. Telescopes like the Hubble Space Telescope capture faint photons that have traveled for billions of years across the vacuum of space. Each one of those ancient beams carries a message, a story encoded in its color, its wavelength, its energy. By analyzing them, we decode secrets about galaxies, nebulae, black holes, and the early history of everything. A tiny redshift in wavelength can tell us how fast a galaxy is retreating. A subtle dip in brightness might reveal a planet passing in front of its star. A strange, faint background glow? It could be the last whisper of the Big Bang itself. And the miracle? All these photons from the distant past, from the farthest reaches of time, still follow the same rules as the light bouncing off your coffee mug. That's the power of a universal constant, whether it's a photon from a galaxy 13 billion years ago, or one reflecting off your kitchen spoon. It moves at the same exact speed, unchanged, unbroken, unwavering. So the next time you open an app or look up at the moon, pause for just a second. There's more happening than you see. A quiet, graceful dance of photons and fields. A choreography governed by laws that never sleep, the same tireless motion, the same quiet rhythm, the same faithful number, 299,792,458 meters per second. Light isn't just a cosmic phenomenon. It's in your home, your eyes, your pocket. It's everywhere, and it's always on time. It's the quiet engine of the everyday. Take a moment, if you will, to imagine a single beam of light drifting through the vast emptiness of space. No planets, no stars, no gravity pulling at it. Just one solitary photon gliding effortlessly through the vacuum, neither speeding up nor slowing down. It has no mass, no rest, and no need for fuel. It simply exists in motion, moving at the only speed it knows, 299,792,458 meters per second. That image, simple and serene, is more than just a poetic thought. It's a glimpse into the very fabric of the universe. Because this humble little beam of light is doing more than traveling, it's participating in the great cosmic symphonia, dance of information, energy, and time that weaves together the structure of everything we know and everything we are. Let's begin with one of the most awe-inspiring relics of light's legacy, the cosmic microwave background, the CMB. This isn't just a fancy term scientists toss around. It's the oldest light in the universe. It has been traveling unbothered and undisturbed for nearly 14 billion years. This faint, uniform glow fills the entire cosmos. It doesn't come from stars or galaxies. It's the cooled-down remnant of a time before there were even such things. About 380,000 years after the Big Bang, the universe had finally cooled enough for atoms to form. Before that moment, it was a dense fog, chaotic, hot, and opaque. Photons couldn't travel far without bouncing off charged particles, but once neutral, hydrogen atoms appeared. That fog lifted. The universe became transparent. And so, the light was free to move, and move it did, in all directions. A sea of ancient radiation that has been stretched by the expanding universe into soft microwave whispers. When scientists detect the CMB today, they're catching photons that have never rested, particles of light that have crossed unimaginable distances just to gently land in a detector and say, here's what it was like back then. That's not just history. That's cosmic archaeology. But the story doesn't end with the past, because light doesn't only tell us where we've been, it also shapes everything we're experiencing right now. From the way stars shine to the way atoms bond. From the spark of life in a seed to the pulse of data in a cable. Light is the silent, invisible participant in every process around us. Consider photosynthesis the green heartbeat of the natural world. It all begins when sunlight strikes a leaf. Photons collide with chlorophyll molecules, exciting electrons, and triggering a cascade of reactions that store energy in chemical bonds. Plants use this energy to grow. Animals eat the plants. Other animals eat those animals. And so the chain continues, spinning upward from the energy of light. Without photons from the sun, there is no photosynthesis. Without photosynthesis, there are no plants. And without plants, well, dinner would get far less interesting and far more impossible. In a very real way. Every meal you've ever eaten began with a photon from the sun, but it doesn't end there. Because our own bodies, our circadian rhythms are deeply tuned to light. Sunlight regulates our internal clocks, our moods, our sleep, our sense of time itself. A burst of morning light signals your brain to stop producing melatonin, the hormone that lulls you to sleep. As evening comes, the fading light allows melatonin to rise again, guiding you gently toward rest. Even now, as you listen to this quiet unfolding of thought, your body is syncing with the light around you, adjusting. calibrating, resting. You are a living sundial, constantly tuning to the brightness of the world. But perhaps the most poetic gift of light is this: it connects, not just eyes to objects, not just telescopes to stars, but moments to each other. Every time you see something, a leaf shimmer, a friend's face, a starlit sky, you're receiving a message, encoded in waves, shaped by the contours of space, translated by your mind. Dot light is the language of the universe. And like any rich language, it has dialects. There are wavelengths that tell us about the chemistry of stars, others that whisper warnings about gamma-ray bursts, the most energetic events in the cosmos. Some carry the heat of newborn stars in infrared. Others scatter into rainbows on oil and soap, revealing the hidden mathematics of color and curve. Light speaks. It always has. And in every glimmer, from the earliest photons of the Big Bang to the soft golden flicker of a candle in your room, it speaks the same truth, one constant, unwavering. Cosmic pulse, 299,792,458 meters per second. And never once has it broken that promise. Interference and refraction. This diversity is what makes light so powerful. It doesn't just show us what's there, reveals how things work. Split beam passed through a prism becomes a symphony of color. The white light unravels into rainbows, each wavelength telling a different part of the story. The flash of a distant supernova carries the fingerprints of heavy elements, forged in the violent furnace of a dying star. Carbon, iron, gold, all born in the eye. Chaos, then flung into space. But what's more remarkable than light's beauty is how we've learned to listen. With radio telescopes, we hear the soft whispers of ancient hydrogen clouds. With X-ray telescopes, we see the hidden skeletons of galaxy clusters. With infrared instruments, we peer through clouds of cosmic dust and watch stars take their very first breaths. We've even built instruments that don't detect light at all, but instead, the subtle ripples in space-time, gravitational waves. Another messenger, another voice, completing the story that photons have always been trying to tell us. And together, all these voices paint a different kind of picture, not a cold, silent void, but a universe that sings. A universe full of signals, full of stories, full of light. And perhaps the most humbling part is this: we are not separate from it. You are not merely watching from afar. You are bathed in this light, shaped by it, made from it. The atoms in your bones were forged in stars that lived and died billions of years ago. That light traveled across space, igniting gas clouds, seeding new systems, and eventually becoming the carbon in your cells, the calcium in your teeth, the iron in your blood. You are made of star stuff, and it was light that brought it to you. So this restless traveler, this photon, with no mass, no rest, no destination, is doing more than moving. It connects the ancient past to the living present. It ties galaxies to skin. It lets our eyes see and our minds understand. In a universe so vast and full of silence, light is the constant companion, not just fast, not just fundamental, but familiar. It's the gentle thread that turns space into story, that fills the dark with meaning and whispers across the emptiness. I am still here. So tonight, as you settle in and your thoughts begin to drift like starlight, remember this: even in the quiet, even in the dark, light is always on its way. And now, gently, we return to where we began. We set out with a simple question: why does light have a speed limit? And along the way, we wandered through fields of photons, danced with electromagnetic waves, listened to the cosmos, watched time bend, space stretch, clocks slow, and galaxies whisper across time. We followed light through cables and clouds, through your phone and your eyes, through the warmth of a leaf and the silence of the stars. And the answer, in the end, is both simple and profound. Light travels the way it does because the universe is built to let it, and to be shaped by it. Speed is not just a number, it's a rule. A cosmic law that holds the rhythm together from atoms to galaxies. It can't be broken. It doesn't need to be faster, because maybe, just maybe, it's already perfect. Just the way it is. And now, as this quiet journey comes to an end, let me ask you one more time. Where in the world are you listening from tonight? And what time is it right now? Are you curled up in bed with starlight spilling across your window pane? Or sitting quietly on the other side of the world as morning light begins to bloom? Wherever you are, and whenever this moment finds you, thank you for spending it with me. If this video helped you breathe a little deeper, or sparked even a small quiet wonder, I'd be grateful if you gave it a like and tapped subscribe. It helps others find their way here to this calm little corner of curiosity. And if this video didn't put you to sleep, at least, maybe you learned something beautiful while waiting for rest to find you. Until next time, rest well, and may your dreams move at just the right speed.